Wonderful. Thank you so much. So we're here to talk with you today about how Kaskada and Redis are partnering to bring state-of-the-art solution in feature generation and feature serving, where Kaskada powers the feature generation, and you all know Redis as a production quality, production ready database and cache, making it a great use for serving features in production. So in this session, you're going to learn how to create and operationalize ML models using Kaskada and Redis directly from event-based data. But first, I want to start with a story. And it's one we've all experienced from a consumer perspective in the last almost 2 years now. The pandemic hit and items flew off the shelves. We didn't yet understand what was going to cause exposure. Many couldn't risk going to the store at all. And I remember I was staying at a friend's house. I was waiting to close on a new home. I didn't even have a place to live. And not even the city was open to process closing paperwork. So on any given day, we couldn't know what would be on the shelves when we reached it. The tenants in that building actually began taking this box and doing a take an item, leave an item in the lobby, because some folks had toilet paper, but some other folks didn't have mac and cheese for their kids. And when we went to the store, we had to think really long and hard about it. Was the exposure worth it? And so I don't know about you, but I began doing most of my shopping using apps like Instacart to try and reduce our risk, and also the time, honestly, it took to search many different stores for the items we needed and finding different things in different places. But it turns out even with companies like Instacart at the start of the pandemic, the item availability models were not predictive. Time and time again, I still couldn't get the items I needed hours later. So the part of the story, though, that you might not know is why it happened and how the delivery trends impacted the inventory systems. So why did it happen? Shoppers saw a 30% drop in the ordered items being actually found when shoppers arrived at the shelves. And that changed over the course of a day. When restocking times increased, the models that predicted availability over the course of the day was no longer predictive. The signs on the shelves that you saw on the last slide became the new normal. I mean, I think I remember Costco even had a whiteboard out front where they were listing items where they were radioing saying, oh, this one's out of stock. Don't even have them enter the store to look. And so it was more than that. It wasn't just restocking times. Store hours changed, workers fell ill. The ability to restock with social distancing orders in place was very difficult. And all of this happened while the order basket size for all customers increased by 35% month over month. So of course the models were no longer predictive because the environment itself around the model, it changed. But it's machine learning. So why didn't the models adapt? And it turns out it's because the models can only be as good as the data we've given. We've heard from multiple speakers today the need for learning from the right examples and the right points in time. This is a problem we're trying to solve. But if the models need to be retrained and fast, how can we adapt more quickly? Why is it taking so long to become predictive? It's because it's critical that the models learn from the right examples. And in this case of item availability during a moment of crisis, in the context flooding the algorithm with examples outside of the exact correct examples is just noise. It can't learn. And so companies like Instacart spent years building a carefully choreographed string of machine learning models to predict demand, understand capacity, and make order dispatching decisions just in time. And they used to work. But all of the models were thrown out the door and they were completely out of whack. And so this idea of if we couldn't have predicted that this pandemic was going to happen, and we wouldn't have known what was relevant to already have the data pipelines built, what if we don't do that? What if we collect everything? What if we compute our models directly from event-based data? And this isn't a wild idea. It is in fact what many of you are doing with customer data platforms like Segment and Heap. If you collect all the data, you don't have to be right up front. You can defer your decision. This motivates why you would want to create models directly from event-based data. I don't have to choose. I don't have to be right. But now that I've said that, Timur is going to talk about the other half of this problem.
Thanks, Charna. I mean, so computing the right data is only half the problem, right? At the start of the onset, we saw and witnessed teams, tripling the number of times at which they're actually running these models for item availability. And, you have to recompute these things, and doing it every 2 minutes is just not enough to get the true understanding of your fulfillment capacity. So the cycle time in being able to recompute these features also significantly reduced. What that means is there's going to be a significant amount of load on the systems that actually recompute these features and actually then give a true state of the fulfillment capacity. And so now you're talking about low latency and high throughput in the underlying systems to be able to support that. So you don't have this panic situation with limited toilet rolls, right? When it comes to item availability, latency is an outage. And so if you look at the customer experience, if you ordered an item and a shopper is not able to fulfill it, from your perspective, that's an outage. And so it's really important to understand the importance of latency and how that feeds into the overall customer experience. Now, when you're trying to look at the availability and scoring it across 500 million items, that's a significant amount. And every item has anywhere from a few hundred features, right? You're talking about massive influx of new data that you have to take a look at. And you really have to think about systems architectures underneath that can support this.
So this is really a complex problem. Needing the ability to adapt quickly and learn from examples that aren't available simply by computing on monthly, weekly, or daily boundaries isn't enough. And once you know what's predictive, you need a low latency, high throughput feature store to keep up with scoring for rapid predictions. But let's take our item availability example further. This talk is about creating and operating ML models from event-based data using a feature engine and a feature store. So we'll be using item availability throughout the rest of the talk as our case study. And we're going to begin with the first half. So computing the right examples for your ML models to actually be predictive. And like we said before, what you really want is to collect all of your events. This is because ML failure stories always end in this way. When the environment around us changes, it goes something like this. I wish I could have known what we know now when we started. I wish we could build a time machine to go back and tell our past selves what we needed to know, to collect the right data at the right points in time in the past so we could solve this problem today. But that's the wrong lesson. And just like Marty McFly in Back to the Future, erasing your lessons learned by preventing the lessons in the first place isn't the goal. Simply sharing your features through a catalog isn't enough. If you collected all of the features at all of the possible snapshots, at all of the possible row level events, it's not enough. You need a system that allows data scientists to describe the choices to learn from as part of the feature definitions and the model context. So now that I've said that, let me hand you off to Davor to talk about some of the time travel trends we're seeing.
Thank you, Sharna. You have seen so far kind of the model availability, item availability model that we kind of gone through. And this may sound like a contrived example, like pandemic happens once in 100 years, but it really isn't a contrived example. Event-based data really contains gold, and that gold is the temporal relationship of the events that exist in the data set. And there are other companies that publicly talked about how they're able to build models directly from raw event-based data, and they've realized a large impact on the business, right? And some of the companies mentioned here, with a large teams of data and infrastructure engineers, really needed to build a limited version of a time machine for their data scientists. This is the key thing, a limited version of time machine for their data scientists. So you don't need to trust our story with the item availability model. There is plenty of examples where we know the teams have found material success by leveraging the gold, which is the temporal relationship of event-based data. But here I want to make one more point. What happens to the infrastructure once we start leveraging event-based data? Over time, the amount of ad hoc data requests starts growing like crazy. I'm sure that some of you have seen this in your teams. If you enable kind of really models from event-based data, there is a growth in demand, typically from data science teams who will want to compute different things and do different experiments. And as the number of models grow, this demand is going to grow. And we all know that our kind of data engineering teams are limited in capacity and super busy, right? And we can only find so many people to hire in any given month, right? And so our ability to deliver all of those features, all of those experiments to build better models tend to be limited. And that kind of the difference in demand to what we can actually, deliver with our limited resources tends to grow, and we expect it to grow more as this technology becomes more available. And so as we make this shift right now, right, as we understand that our data engineering teams are really swamped with a lot of requests for new computations, right? We really have to understand that we have to focus on the instant iterative process for the entire ML team. We need to be able to define experiments and see whether they're good, that they are bad, what we want to do iteratively in a self-serving way. And that is the organizational key to success.
So something needs to change. You're already able to create models from pre-aggregated historical data, but now you need instant iteration on event-based data. And in the past, you would have created a training data set and attempted to use that data to iterate just the features, things like computing importance across various segments of your data, visualizing this and that and all of these different statistics. But to be able to create event-based data models instantly requires a shift to your workflow. It's not just about adding one feature and going back to a specific point in time. There are some key requirements. You have to generate historical feature values to try new features. You have to have expressive time selection to specify your model context iteratively, because it turns out these two things are connected. And joining values between different entities at precise points in time becomes critical when you didn't have to decide up front what's going to be predictive. Finally, you have to have shared feature definitions to power the live models. Otherwise, you're not solving the full problem. It doesn't matter if you found something predictive. So grounding ourselves in this case study, we're building an item availability model and reducing the data to find the right examples. The signal and the noise is key. So you can begin to see improvements by simply shortening the windows where you're computing or computing more frequently, but it's not enough. The y-axis here is the item found count, and the x-axis is the time in terms of events as well as clock time. This is because the important times are different for every single store. There is no global time availability that you could simply snapshot and go back to. This is a data-dependent point in time for this store, and it needs to be computed arbitrarily across time, discrete or continuous. So as you look at the x-axis for this one store and item, you'll see the events with store open, item found, item not found, restocked event. And this is going to change over time. And the gold is found in the events relative to each other. So the first key requirement is to define what to compute in your instant iteration. Feature one here could be the time since the time the item was last found. And so for every item, there will be a history of events. The language needs a way to express these relationships. This isn't the first pandemic or historical event that you could learn from if you're collecting everything. Hurricanes, earthquakes, epidemics globally have been causing items to fly off the shelves for a long time. So we'll also need a way to express what events to include, not just by their clock time. In the past, feature engineering from pre-aggregated pipelines limits what you can compute, what you can learn. Feature snapshots limit what you can learn from as well to specific points in time. Here, you no longer need to know ahead of time what data points to collect at what points in time in order to train the model. But it's not just about what, it's about when. The second key requirement then for instant iteration is the ability to select when to compute. In the real world, it's part of model context. Critically, when to compute isn't just clock time, it's data dependent as well. If you're computing your features, you also need to compute your labels at meaningful times to produce training data sets. And ideally, for instant iteration, a quick code change is all you need to produce the full history of a new computation to enable rapid testing. So in this example, prediction times for item availability will need to occur when customers are browsing the app, when the cart is submitted, and when a shopper begins shopping during a catastrophic event. Those event times are not global either. We're shopping at all hours of the day. So browsing late at night can happen, I do this often at 11 o'clock at night, and it happens within many time windows during the day. And this is part of what is part of the training data set is when to compute. So in the past, waiting for new features, data to be collected, or complex backfill jobs to compute means more customer outages while you wait for the computation, just to see if the idea might be helpful. And in this new world, you can iterate on what to compute and when to compute it iteratively to build up the model context and features. The third requirement we have is what may sound initially like, well, why do I need this? Is the ability to look up information from multiple entities. The key features to predict an item's availability may include events on other entities, information about the retailer, the shopper, the region, and buyer entities are critical, actually, to predict item availability. And when you're computing directly from event-based data and you haven't defined your entities ahead of time, you need to provide the ability to group by different entities and join at precise points in time without leakage. It's critical. Operating on the results from a feature store or for a data pre-processing pipeline is the leading cause of leakage and underperforming models in production. This after seeing amazing performance in the lab. And for real-time applications, computing only at row-level feature store times isn't enough. In the past, you would have had to find a way to line up both row-level event times and discrete data and features computed at continuous times via some level of time truncation, inherently limiting the accuracy and performance of the model. With a native time travel feature engine, you'll be able to recompute features at different points in time to see that your model will be more predictive. And you still may seem like enough. We found the most predictive features. These are the things we need to look up to predict item availability. But you need to actually put your models into production to test how predictive it is today.
Yep, and that's right. I mean, you can have the most predictive features and find the most predictive features, but if you're not rescoring quick enough and fast enough, you'll be left with an empty cart, and that's what you don't want to do for a consumer. When it comes to forecasting supply and demand, one of the key things to keep in mind is latency is an outage, right? And it doesn't matter what product or service the end user is in need of, whether it's a toilet roll or whether it's formula for an infant. Our dependency on these things is so high that we need to have instant availability, right? But getting models into production for real-time inferencing is a difficult thing to do. Forrester Consulting and Redis, we did a survey, and 40% of the decision makers agree that their current architectures are unable to meet the future demands of machine learning. So there's high demand for real-time model inferencing, but it does uncover and expose a number of challenges when it comes to accuracy, latency, and reliability. And when you can run the ML model inferencing, in the database where you can co-locate the data and the models, right? You can address a lot of these critical challenges when it comes to latency and reliability. What we'd like to do is actually walk you through an architecture here, and Charna and I will actually walk through the different aspects of it. But when you actually look at the underlying architecture, it needs to support a number of things, right? So being able to have iterative feature engineering, an end-to-end inferencing solution, no downtime, scalability. And at the same time, you want to be able to have ease in which you can put new models into production. Monitoring is equally important as well too, because the more effectively you can monitor, the quicker you can learn from that and then recalculate features to meet that demand. Charna, I'll turn it over to you.
Perfect. So we'll start with the first step. Here you'll see that Kaskada is connecting directly to the event-based data to instantly compute new features at those arbitrary data-dependent points in time. This is done in a data scientist's favorite environment, even in Jupyter, where Kaskada supports ad hoc queries during exploration that are not persistent until they've been able to train a model they'd like to try in production. Then in a persistent view of the group of features is created to be computed at scoring time, incrementally in this case, to keep the online feature store up to date. Timur?
And once you've had these features computed, you can put them into Redis, which can be an online feature store for low latency storage and serving. At the same time, with solutions like Redis Enterprise, where you can actually store the data on flash, you can store larger data sets and then actually use it as an offline store. Even though you may have existing solutions like data warehousing solutions, such as Spark, Databricks, or Snowflake, this is another option for low latency storage across higher data sets. Once you finally have this, then you could use Redis as a model store, where you can actually store the binaries, metadata, and various artifacts that can really improve the overall delivery of features being delivered to the models. And then as you take it a step further, this could feed into the inferencing. Redis AI is an inferencing module where it actually co-locates the models with the data, but you could actually do the serving through any other solution there. And the more you can instrument and add monitoring capability, another manifestation of using Redis is as an evaluation store. You can actually store the model performance data. And with all these different instantiations of how Redis can be used as a primary data layer in the production stage, combined with Kaskada, you can actually close the entire loop. So you do actually ensure that your features are live, fresh, and fast. At the same time, this not only improves the inferencing capability, which we'll talk about over here, is once you're dealing with large amounts of data, you really need to drive higher throughput, right? You might have 5 million, products, but then when you combine that across, 25,000 different store locations, the data increases. And what this shows is with Redis AI, you can scale linearly to actually meet the high throughput requirements. At the same time, when you look at latency, it's very important to make sure that, in the case of item availability, once the load on the system, if you look at the 500% year-over-year increase in just the volume of orders, you really want to ensure that you can deliver that in low latency. And what this really shows here is that as the number of clients increase and the data set increases, a solution like Redis AI can really ensure low latency serving.
Cool. I do have a demo for you, but it looks like we have 1 minute and 11 seconds left. So I'm going to save that because I think we're going to have some questions, and let us do our recap first. We will be doing a webinar showing this full demo, and we can absolutely walk you through it. But let us do our recap first, because I think it's important to land all of the narrative, and then if we have time, we'll go back to the demo. So in summary, creating models directly from event-based data means you are not making decisions that limit your experimentation. You have so many more choices, so many more options and applications, and it allows you to build models that actually work. I have heard from customers time and time again, I have tried to solve this problem before. Why is it different now? But it's different because you can learn from the right examples at the right points in time. But it does increase the demand for your event-based data. And to keep up, you need instant iteration with a feature engine that can enable your data scientists to compute directly, express what and when to compute, and support some temporal streaming joins, as well as serve the same features in production.
And operating models from event-based data, you want to really eliminate the data discrepancies in production with shared feature definitions. ensuring that you have low latency and you can run that inferencing capability to meet the demand and really address the real-time throughput needs for a high throughput feature store.
And so for me to summarize, I think I should say that really solving this problem is possible today. Kaskada and Redis have proved this, and we are happy to answer any questions you might have on how to put this into practice. So please, don't hesitate to ask more questions.